Welcome to the Deep Dive. We're here to break down complex research into insights you can actually use. Today, we're diving into something really fundamental in automotive engineering, especially now with electric vehicles taking over. It's all about how the power gets to the road. The shift from combustion engines to electric, well, it's shaking up how cars are designed from the ground up. We're asking that core question for EVs. Should they be front-wheel drive, FWD, rear-wheel drive, RWD, or all-wheel drive, AWD?
Exactly. And for this deep dive, we're leaning heavily on a pretty detailed comparison thesis from researchers at the Politecnico di Torino. They use some really sophisticated simulation tools to properly measure everything: consumption, cost, performance across these different layouts. So our goal here is to kind of cut through the jargon and understand the real technical trade-off they uncovered.
Okay, good. Because you hear a lot about AWD in electric cars.
You do. And the market definitely seems to prefer AWD or four-wheel drive for EVs. People like the better handling, the safety, the traction. And what's interesting is with EVs, adding that second motor for AWD doesn't necessarily hit your energy use as hard as it would in a traditional car. It's a different calculation.
Right, unlike adding drive shafts and differentials in a gasoline car.
Okay, let's unpack this.
But before we even get to which layout is best, there's a story in how they even managed to do the research efficiently.
Ah, yes. The simulation speed. That was critical.
So the researchers were using the standard test, the WLTP cycle. That's the worldwide harmonized lightweight vehicle test procedure, right? Super important for figuring out EV range and efficiency.
That's the one, the industry standard. But they ran into a problem, a big one.
It was taking too long.
Way too long. We're talking over 10 minutes,
Yeah.
720 seconds to be precise, just to run one simulation cycle using their initial model.
Wow. And if you want to test lots of different setups, like different power splits for AWD, 10 minutes a pop is just not workable.
Exactly. It totally limits your ability to explore the possibilities. The bottleneck was essentially the complexity of their model.
What kind of model were they using?
It was called a four-wheel double-track model.
Hmm.
You can think of it as a very detailed digital twin of the car. It simulates everything, all four wheels independently, steering angles, how the body rolls in corners, side slip, the works. You need that detail if you're simulating, say, aggressive cornering.
Okay, so very complex physics involved.
Very complex. Especially the tire models, they were using these things called Pasejka magic formulas, which are standard but computationally heavy, plus loads of lookup tables for data.
But then they had an insight, right?
They did. They realized, wait a second, the WLTP test cycle, when you run it in the lab on rollers, the car's just going straight. There's no steering involved.
Ah, so if there's no steering.
You don't need to calculate all the complex physics related to cornering.
Yeah.
Things like side slip or body roll become pretty much negligible.
So they could simplify.
Radically simplify. They ditched the four-wheel double-track model and moved to what's called a single-track, or sometimes a bicycle model.
Bicycle model. Okay, explain that.
Imagine collapsing the car down its center line. You treat the front wheels as one combined wheel and the rear wheels as another, like a bike, but with the car's mass and inertia.
I see. So you still capture the forward motion, the acceleration, the braking.
Precisely. You get the longitudinal dynamics you need for a straight-line consumption test, but you throw out all the lateral dynamics calculations that aren't relevant here.
That sounds incredibly clever, just focusing on what actually matters for this specific test.
It's smart engineering. They also streamline some other things, like removing unnecessary data logging.
In the result, what was the speed up?
It was significant. They cut the simulation time by 25%, down to about 542 seconds. Still not instant, but much, much more manageable.
That 25% gain must have made a huge difference for their ability to actually compare all the different configurations properly.
Absolutely essential. It opened the door to really dig into the efficiency details, especially for AWD, which brings us to their main findings on consumption and cost.
Okay, so with the faster simulations, they could really explore how efficient these different layouts are. Now, AWD in an EV has this theoretical perk, right? Intelligent torque allocation.
Yes, that's the big promise. The car's brain can decide, millisecond by millisecond, whether to send power to the front axle, the rear axle, or both, specifically targeting the most efficient operation at that exact moment.
So what did the WLTP cycle simulations show? Did AWD live up to that promise?
It did, but with a twist. Something quite counterintuitive actually came out of the consumption analysis.
Oh, what's that?
The most efficient way to run an AWD system is not a perfectly balanced 50.40 power split between the front and rear axles.
Really? I would just assumed, share the load equally. That's got to be best.
You'd think so. But It boils down to how electric motors work. Every motor has an efficiency map, combinations of speed and torque where it operates best, its sweet spot. If you have two identical motors, and you ask both to deliver a small amount of torque, they might both be operating quite inefficiently. The AWD system can be smarter. It can say, okay, for this amount of torque needed right now, it's actually more efficient to send most or even all of the power to just one of the motors, letting it run closer to its peak efficiency point.
Ah, I see. So it's better to load up one motor effectively than to underutilize two.
In many situations, yes. That's why the simulation showed the points of minimum consumption. The best efficiency often occurred with really uneven asymmetric splits.
Like how uneven?
We're talking things like 15% of the torque going to the front and 85% to the rear, or the other way around, 85.15.
1585. That's basically acting like a rear-wheel drive car most of the time, but with a little help from the front.
Kinda, yeah. But the beauty is that the optimal split actually changes depending on how much power you're demanding. Well, the study found that as the total power needed drops, like when you're cruising steadily at lower speeds, the most efficient split tends to move closer to an even distribution. Maybe not 50.50, but more like 30.70 or even 40.60.
Okay, so the AWD system gives you that flexibility to always find the best operating point, whereas a simple FWD or RWD car is just stuck with its single-driven axle.
Exactly. It offers optimized efficiency across a wider range of driving conditions, plus you still get the traction benefits when you need them.
Makes sense. But efficiency isn't everything. What about the cost? Adding a whole extra motor and power electronics must add up.
Oh, absolutely. From a pure component cost perspective, 2WD, whether it's front or rear, is undeniably cheaper. Fewer parts, simpler setup.
No surprise there.
But the study did something interesting. They looked at the total vehicle cost, including a reference battery that used a 90 kilowatt pack, which is pretty substantial.
And when you factor in the expensive battery,
The cost difference between a 2WD and an AWD powertrain suddenly looked much smaller in percentage terms. Often, the premium for AWD was only around 5% of the total vehicle cost.
only 5%. That's less than I might have guessed. Still, 5% on a, expensive EV is not pocket change.
True, it's still a cost increase, but it puts the trade-off into perspective. You're paying maybe 5% more for potentially better efficiency in some scenarios, plus significantly better performance and traction, which we'll get to.
Is that 5% premium worth it just for the potential energy savings, or is it more about the performance?
That's the million-dollar question for designers, isn't it?
Yeah.
The study suggests the efficiency gains alone might not always recoup the extra cost, but when you add performance, that changes things. And don't forget weight.
Right, the AWD system adds weight.
Yep, about 50 to 70 kilograms heavier than the 2WD versions in their simulations, mostly the extra motor, inverter, and associated bits, and weight is always the enemy of range.
So it's this constant juggling act. Cost, weight, efficiency, performance.
Oh, it's
Okay, let's talk performance then. The fun stuff. They looked at acceleration, right? 0 to 100 kilometers per hour.
They did. The classic 0-100 kilometer sprint and also the 80-120 kilometer elasticity test, which is a good measure for highway overtaking power.
And I bet AWD shines here.
Oh, absolutely.
Yeah.
Especially when you start dealing with higher power levels. They tested up to 270 kilowatts, which is quite a bit of power.
What happens with FWD and RWD at those levels?
They just run out of grip. Simple as that. They hit the tire traction limit really quickly. You stomp the accelerator, and the tires just spin because they can't physically transmit all that torque to the road through only two contact patches.
So you get wheel spin instead of acceleration.
Exactly, which obviously slows you down. AWD, though, it just solves that problem. By splitting the torque demand across 4 tires instead of 2, it dramatically increases the total amount of force the car can put down onto the pavement.
Makes perfect sense. More grip equals faster acceleration.
The results were clear. Significantly quicker acceleration times for the AWD configurations, especially at higher power.
Okay, so AWD wins for outright acceleration if you have enough power. But what about the 2WD options? We see a lot of sporty EVs going for rear-wheel drive. Why RWD over FWD for performance?
There's a solid physics reason for that. It's not just tradition. RWD consistently performed better than FWD in the acceleration tests, even when traction was the limiting factor.
Why is that?
It's due to dynamic weight shift. When you accelerate hard, what does the car do? The nose lifts and the rear squats down, right?
Right, the weight shifts backward.
Exactly. And that shift puts more vertical load onto the rear tires. More load means potentially more grip. So the rear tires on an RWD car can actually handle more torque during acceleration, precisely because of this weight transfer.
Ah, so the act of accelerating actually helps the RWD car put its power down better.
Precisely. FWD has the opposite problem. The weight shifts off the driven wheels, reducing their grip potential just when you need it most.
And there's another benefit to RWD for sporty driving, isn't there? Something about steering feel.
Yes, that's crucial too. With RWD, the front wheels are only doing the steering, not also handling the power delivery. This means the forces coming through the steering wheel are cleaner, giving the driver better feedback.
Whereas FWD can suffer from torque steer.
Right, torque steer is where the high torque going through the front wheels tries to pull the steering wheel left or right, especially if the grip isn't perfectly even. It's not ideal for performance driving feel.
Okay, so the performance picture is AWD is king if you have high power and want maximum acceleration. But if you're sticking with 2WD, RWD has inherent advantages due to weight shift and cleaner steering dynamics.
That sums it up nicely, yes. Hashtag tag outro.
So bringing this all together,
Yeah.
what's the big takeaway from this research? It sounds like choosing the best EV powertrain isn't simple.
Not at all. It really confirms that it's a classic engineering compromise. It depends entirely on what the primary goal for that specific vehicle is.
If cost is absolutely the number one priority.
Then you probably stick with a simpler, lighter 2WD layout, either FWD or RWD, lower component costs, less weight.
But if you're chasing maximum performance or you want that optimized energy efficiency you get from the really clever torque allocation,
Then AWD becomes the clear winner, especially once the power levels get high enough that 2WD systems start running into those traction limits we talked about.
and the research specifically showed that just a generic 50.50 AWD split isn't the magic bullet for efficiency, right?
Correct. The simulations suggest that a simple 50.50 split is often less efficient and potentially more costly in terms of components than a really well-optimized asymmetric AWD system that constantly adjusts the split. Sometimes even a basic RWD setup might be more efficient than a naive 50.50 AWD.
Yeah, you look at some major EV makers, like Tesla, for instance, they often use the same motor unit on the front and the rear axle in their dual motor cars. That kind of implies a default 50.50 hardware capability.
That's a very important point, and it leads us out of the pure simulation world and into manufacturing reality.
Because this research, detailed as it was, didn't really factor in economy of scale, did it?
Exactly. Think about it from a car company's perspective. What if you could design just one standard excellent motor and power electronics unit,
Okay.
and then you just install that same unit on the front axle for an FWD car, the rear axle for an RWD car, or on both axles for an AWD car? A fixed 50.50 hardware set up by default.
You'd save a fortune in design, manufacturing, inventory, logistics, building just one core component instead of multiple variations for asymmetric systems.
Massive potential savings. And so here's the final provocative thought for you to chew on. Could those huge savings from mass-producing a single standardized powertrain unit actually outweigh the small, measurable loss in energy efficiency that the simulations show compared to a theoretically perfect but much more complex custom asymmetric AWD system?
That's the real world trade off, isn't it? Balancing peak technical optimization against the practicalities and costs of mass production. It's not always about squeezing out that last zero point 0.1 kilowatts per 100 kilometers.
It rarely is in the real world. There are always other factors at play.
Well, this has been fascinating. A real journey from simulation optimization to the nitty gritty of powertrain choices. Thank you for walking us through it.
My pleasure.
And thank you all for joining us for this deep dive. We hope you feel better equipped to think critically about how electric cars are put together and the choices engineers are making for the future.